So in this example, we have to find the orthogonal matrix P such that P inverse AP is a diagonal matrix. So chalo, let us begin then. So I have already done few calculations for you which are routine work actually. So this is a matrix. You can observe that this is a real symmetric matrix. So this is going to be orthogonally diagonalizable by using this note. So therefore definitely we will be able to find orthogonal matrix P such that P inverse AP is a diagonal matrix. So what I have done is I have found out the characteristic equation of this matrix. Then by doing certain calculations you get the eigenvalues to be 0, 1, 6. Now I found out the eigenvectors corresponding to each eigenvalue. First of all, I went for lambda is equal to 0 and I got this eigenvector, that is 1 minus 2 1. Then thereafter I went for lambda is equal to 1 and I got the eigenvector. Now just note one thing, for lambda is equal to 1 I came across one interesting thing while using Cramer's rule. Now see here, we cannot use first row and second row for Cramer's rule in this case, because both the rows are linearly dependent, because if you multiply first row by minus 2 you will get the second row. So therefore it should be either used for first or third row or second and third row. Over here I have used second and third row in order to find the eigenvector, and you can see that I got my eigenvector to be minus 2, minus 1 and 0. Similarly for lambda is equal to 6, I went for the calculations and I got my eigenvector to be minus 1, 2 and 5. So this is a routine work that we already know. Now the question is, we have to find orthogonal matrix P such that P inverse AP is a diagonal matrix. Just now I have explained you what are the properties satisfied by the orthogonal matrix. So the columns of the orthogonal matrix are what? Orthogonal to each other. That is the first thing to note. And the second thing is that norm of each row and each column is also 1, right? So that should be satisfied in order to get orthogonal matrix P such that P inverse AP is a diagonal matrix. And as well we know that the eigenvectors corresponding to distinct eigenvalues of a real symmetric matrix are orthogonal. See this, eigenvectors corresponding to distinct eigenvalues of real symmetric matrix are orthogonal. So over here, since this is a real symmetric matrix and all the eigenvalues 0, 1, 6 are distinct, so whatever eigenvectors we got, they will be orthogonal. We can check that. So actually first eigenvector I got corresponding to 0 is 1 minus 2 1, and the other one over here I got minus 2 1 minus 2 1 was the first one, right? And over here I got minus 2 minus 1 and 0. So just check whether they are orthogonal or not. So 1 multiplied by minus 2 is minus 2, minus 2 multiplied by minus 1 is plus 2, and 1 multiplied by 0 is 0. So your answer is 0. So you can see that these two vectors are orthogonal. Similarly you can check that this first and the second one, minus 2 1 0, remember that I have used notations over here. The corresponding to 1 eigenvector आहे तिला मी x2 म्हटले, corresponding to 0 जी आहे तिला मी x1 म्हटलेलं. I will just show you. Yeah, I am calling it as x1 over here, and corresponding to 6 जी eigenvector भेटलेली आहे मी त्याला x3 म्हटलेलं आहे. Now you can observe that this minus 1, 2 and 5 will be orthogonal to our both the eigenvectors. What are our both eigenvectors? Okay, just I will write it here. I will write it here. Now to find P orthogonal matrix P, right? Now to find orthogonal matrix P such that P inverse AP is equal to what? A diagonal matrix, isn't it? So I will write here, we have x1 is equal to, okay, what are our eigenvectors? Remember, first eigenvector is corresponding to eigenvalue 0, the second eigenvector is corresponding to eigenvalue 1 I guess, and the third one is corresponding to eigenvalue 6. This is important because whatever diagonal matrix we are going to get on the right hand side, the diagonal entries depends on this, isn't it? So our first eigenvector was, I guess, 1 minus 2 1, okay. So 1 minus 2 1, note that it is corresponding to eigenvalue 0. Second one is corresponding to eigenvalue 1, and the third one is minus 1, 2 and 5, and what was the second one? And the second one was minus 2 minus 1 0, minus 2 minus 1. Yeah, so you can check these two will be orthogonal because minus 2 multiplied by minus 1 will be 2, then you are going to get minus 2, which is 0. We already checked first and second. You can check first and third also. Minus 1 minus 4 plus 5, it is also 0. So you can see that all these three eigenvectors are orthogonal. So since we have to construct this P to be orthogonal, we want the columns of this P should be orthogonal. So we already have this x1, x2, x3 to be orthogonal, so it is good. But the question is, I want the norm of each vector to be 1 also. But is that satisfying? Let us check. Okay, so is norm of each vector 1? If I go for norm of first vector, I'll get under root of 1 plus 4 plus 1, which is under root of 6, which is not 1. Similarly, norm of x2, just I will write here. Here, what is norm of x1? Norm of x1 is under root of 1 plus 4 plus 1, that is under root of 6. Norm of x2 is under root of 4 plus 1, that is root 5. And norm of x3 over here is under root of 1 plus 4 plus 25. Okay, and that is nothing but 1 plus 4 plus 25 is under root of 30, isn't it? So the trick over here is, do you know how to convert the vector to a unit vector? I hope you know it, by simply dividing by its norm. So what I am going to do is, I am going to divide this x1 vector by its norm, similarly x2 by its norm, and x3 by its norm. Okay, so I will say we have my x1 cap, isn't it, that is a unit vector corresponding to x1 cap will be equal to what? X1 upon norm of x1, and that will be equal to 1 upon root 6. But I write it like this, 1 upon root 6, then minus 2 upon root 6, and the next one is 1 upon root 6. Okay, then your x2 cap over here is now in this case it is root 5, so minus 2 upon root 5 minus 1 upon root 5, and this is going to be 0, which is well and good. What about my x3 cap? Our x3 cap is going to be minus 1 upon root 30, 2 upon root 30, and 5 upon root 30. Okay, so so what is your orthogonal matrix over here which satisfies that property P inverse AP is equal to diagonal matrix? So it is nothing but what? Just a minute. So here I will say P is equal to what? X1 cap, x2 cap, x3 cap, which is equal to what? 1 upon root 6 minus 2 upon root 6, 1 upon root 6. The second column will be minus 2 upon root 6 minus 1 upon root 5, 0, and the last one will be minus 1 upon root 30, 2 upon root 30, and 5 upon root 30, isn't it? Is orthogonal matrix such that P inverse AP is equal to what? P inverse AP is equal to the diagonal matrix. And what is my diagonal matrix? 0 0 0 0 1 0 and 0 0 6. Okay, and that is what I wanted to prove. So I have found out orthogonal matrix P such that this is happening. Okay, so that's all then for this example. Now you can solve some more examples from our practical. Okay, and the idea is similar. Oh, it should be, I have made some mistake over. It should be minus 1 upon or minus 2 upon root 5. Yeah. Now looks great.